Hello everyone, and welcome to this video that I'm calling the definite integral process. Now, I want you to know before we get started that this video is very conceptual, and we're going to go through this process, and I need you to understand this process perfectly. I need you to understand every little detail of this video. So please make sure you watch it, rewatch it, and rewatch it if you need to, and make sure you understand every little detail, including notation, especially notation. We're not actually going to we're going to do some calculations in this video, but for the most part, those calculations are just to illustrate the concept. We're not going to actually calculate anything that's important in calculus in this video. But the point is, as we go through our calculus course, we're going to be calculating lots of things that follow this process. So that's why I want to make sure we just have one video where we just talk about the process and that's it. Okay, so a couple of things real quick before we get started with the video. First thing is there's two types of integrals. One of them is called an indefinite integral, and the other one is called a definite integral. So I just want to talk about three things here. First, I want to talk about notation for each of these things. Then I want to talk about how you calculate each of these things, and then what each of these things mean. Just to make sure we're clear on the difference here. So for an indefinite integral, the notation looks like this. So you have this fancy looking symbol over here to start it out, which is supposed to really look like an elongated S. And then on this side we have a dx. And then in between we have a function. So that's the notation for an indefinite integral. A specific example is something like this. So again, we have this integral. So this is called the integral symbol. Again, it looks like an elongated S. We have a dx here and some function. In this case, the function is f of x equals x squared. That's the notation for an indefinite integral. For a definite integral, the difference is you're going to see numbers on the integral sign. So for a definite integral, the notation looks like this. Okay, so again, we have this fancy integral symbol, but now there are numbers. There's a number on the bottom there, and there's a number on the top there. And then we still have a dx on the side and a function in the middle. So the real difference as far as notation goes is for an indefinite integral, we have this integral symbol, no numbers on it. And then for a definite integral, we have integral symbol with numbers on it, top and bottom there. Specific example of a definite integral, something like this. So again, we have the integral symbol here, but you see there's a number on the bottom, number on the top, and then dx over here, and then of course some function in between. So that's the notation, first of all. Okay, second of all, let's go back to the indefinite integral. Just for a minute here. So what does the indefinite integral mean, and how do you calculate it? Okay, so let's just look at this specific example here. So if you have an integral symbol with no numbers on it, a dx here, basically what the meaning is they want you to find all the antiderivatives to the function in between here. Okay, so it's just a bunch of fancy symbols, but basically the thing that's in the green box there, I want you to find all the antiderivatives of that function. Sometimes they also call it the general antiderivative, but since we're using the word integral, indefinite integral, with no numbers on the integral symbol, I'm asking you to find all the antiderivatives of the function in the middle. And you know how to do that. What you do is you write down one antiderivative, use the power rule. So you add 1 to the power, it becomes x cubed. Then you divide by that same power. So you get x cubed over 3. But when I write down x cubed over 3, I've only written down one of the antiderivatives, and I want to write down all of them. So the way you write down all of them is you put plus c. And this plus c stands for a constant. Basically, c stands for a number. So basically the idea is every antiderivative will look like this. But we don't know what c is. In other words, you could plug in any number you want for c, and that'll give you another antiderivative. So for example, x cubed over 3 plus 0. If you change the c to 0, that gives you an antiderivative. If you change the if you change it to x cubed over 3 plus 1, so you change the c to 1, gives you another antiderivative. So if you change this c here to any number you want, then this whole mess is another antiderivative of the function x squared, and in that way we have them all. Okay, so x cubed over 3 plus any number is an antiderivative, and we have listed them all there. That's what indefinite integral means. So that's what it means, and then that's how you find it. You write one antiderivative down, and then you just put the plus c at the end. Now, this video, though, is not about indefinite integrals. It's about definite integrals, but I just want to make sure you knew the difference first. So for an indefinite integral, like something like this, what does it mean? Well, what it means, that's what this whole video is about. So I'm not going to talk about the meaning at this moment, but just let me tell you how to calculate it real quick. There's two ways of calculating a definite integral. We're talking about definite integrals, where there's a number here and a number here. There's two ways of doing it. There's a long way of doing it, which we're not going to talk about in this video, and it doesn't work all the time anyway. It is an important thing to know how to do, and most of the ideas will be in this video anyway. But anyways, there's a long way of doing it. And then there's the short way of doing it, which comes from the fundamental theorem of calculus part 2, which I'm also not going to talk about, except for, to remind you, so this is what you do. So if you're trying to find a definite integral, again, one with numbers on top, what you do is, first thing you do, the fundamental theorem of calculus part 2 says, write down any antiderivative of this that you want, any one. So usually people will write down x cubed over 3, and they just won't write the plus c, meaning they're putting 0 in for c. You can put plus 5 if you want, but it really doesn't matter what number you use for c, so make it simple and just don't put a c at all. And then you put a vertical line here, you put the 1 on top, the 0 on the bottom, and the vertical line means that you're going to plug in the 1 to this function, and then you're going to plug into the 0 to this function, and then you're going to subtract. So fundamental theorem of calculus says do this little thing, and you'll get this definite integral answer. So you plug in the 1 first, you get 1 cubed over 3, minus, then you plug in the 0, 0 cubed over 3. So you have to plug in the top number first, then the bottom, and then subtract. And when you're done, let me clean it up here a little bit. You get that the answer is 1/3. Okay, so that's how you calculate a definite integral. One more time, you find any antiderivative of this you want, then plug in the top number to it. So we found the antiderivative, there it is. Then you plug in the top number to it, then the bottom number to it, and then make sure you subtract. Okay, so the difference between an indefinite integral and a definite integral. Indefinite integral is a bunch of functions, all antiderivatives of this. So it's a whole collection of functions. Definite integral is a number. Notice the answer is a number in the end. So when you're calculating a definite integral, you get a number. So the question is, where does this number come from? What does it mean? Okay, so we know, so now I hope after the end of this slide, we know the difference between an indefinite integral and a definite integral. And this video is all about definite integrals, okay? When you calculate a definite integral, you get a number, but what's the number telling us? Okay, so where is it coming from? Okay, so that's the first thing. All right, so next thing. Why is this video, this process, going to be useful for us? Basically, there's going to be many different quantities in calculus that you're going to want to calculate that all follow this process. So here's a list of a few of them. So finding areas under curves, finding areas between curves, finding volumes, work, which is a physics concept, hydrostatic force, which is another physics concept, center of mass, which is another physics concept, finding arc length, and then we're going to see a few different situations where you find arc length. So one where I give you a function, one where I give you a curve in parametric form, another one where I give you a curve in polar form. Or surface area of revolution, again, there's a couple different situations for that, and then some other areas if it's in parametric form or polar form. So anyway, and then there's lots of other ones that I have not listed here. But in Calc 1, Calc 2, and Calc 3, you're interested in calculating certain of these quantities here. And the deal is, to calculate each of these and others that I have forgotten to list, they all require a definite integral. And in order to figure out what is the volume, what is the area, what is the work done, you have to follow this process that we're going to go through. So it's going to go like this. Some of these quantities, I am going to derive the formula for how to calculate the quantity. And then you can just use the formula, so it's going to be much easier in that situation. But when I derive the formula, I'm going to be using the definite integral process to derive the formula. So in those situations, since you don't need to know how to derive the formula yourself, you won't have to actually go through the process yourself, but I want you to you should still know where things come from. So when you watch me derive the formula, you go, oh, he's going through that process. So in the end of when he's done with this process, we're going to end up with some kind of definite integral as our answer. Okay, so that's the usefulness of this process and this video for me. Now the usefulness for you is there's going to be some quantities on this list, and again, other ones that I haven't written down here, where I'm not going to just give you a formula. Basically what's going to happen is you have to go through the process on your own. And then you're going to go, oh, look, I'm going through this process, so it must be a definite integral. Okay, so one more time, let me say that. So there's going to be some quantities where I'm going to derive the formula, and I'm going to have to go through this process, and you're going to go, oh, so it makes sense that we got a definite integral to do. And there's going to be other problems where I'm not going to go through the process. The student is going to go through the process. And since you have to go through this process, you really have to understand the process. And once you understand the process and you go through the process, then you're able to calculate these things. All right, so that is the plan for this video. So let's get started. Okay, so I've organized the video into 3 parts. The first part is, what is a Riemann sum? We have to make sure we understand the idea completely clear and understand the notation really well. And then once we're really good on what a Riemann sum is, then we have to talk about what the meaning of a definite integral really is, which it's a limit of a sequence of Riemann sums. And then once we get all that done and we really understand everything, then I'm going to end the video with a couple of questions and a couple of comments. All right, so let's do it. Okay, so what is a Riemann sum? A Riemann sum is a very unusual type of sum, but it's just going to show up a lot in the quantities we want to calculate. So I want to show you how this sum works. So let's look at a specific example first. What's going to happen when you're finding a Riemann sum is you're going to be given 2 things. You're going to be given a function and an interval that the function is defined on. So for this example, let's just make the function x squared, and let's make the interval 1 to 4. Okay, so I'm giving you a function, I'm giving you an interval. Also notice, let me just write this down real quick, that if I write down some kind of definite integral, I'm just writing a different one down. Notice what you're given, an interval 7 to 9, and a function. Okay, so anytime you're talking definite integral, or Riemann sum, there's going to need to be an interval and a function. And when it comes to the interval, I want you to think of this interval as on the x-axis. Don't forget, when you have functions have inputs and outputs. So since I'm thinking of the interval as on the x-axis, I'm saying think of the interval as stuff that you would eventually plug into the function. So let's go ahead and draw an x-axis here. Okay, and let's go ahead and calculate a Riemann sum. So here's what you do. Let me go ahead and label the start and end of this interval, so 1 and 4. And what you're going to do is you're going to take this segment here from 1 to 4, and you're going to cut into pieces. So right now what I'm going to do is I'm going to cut into 3 pieces. In order to cut into 3 pieces, I have to put 2 tick marks. Something like that. And you want to make sure that when you cut into 3 pieces, the 3 intervals you get, which I'm going to be calling subintervals for the rest of the video, you want them to be equal width. If they don't look perfectly equal, we're going to have to pretend that they look equal. So I've cut the big interval here from 1 to 4 into 3 subintervals. This one here from here to here, and there's this one here from here to here, and this one here from here to here. Okay, so then I want to figure out where these tick marks are. It's not hard to figure out where they are. You could probably guess right away where they are. If I say, what's the number here, what's the number here, you could probably figure it out right away. But let me just give you a slightly more complicated way of thinking about it so that it'll work no matter what. Because this problem, the numbers are pretty easy, but in other problems, the numbers might not be so easy. So basically the idea is you first figure out how long is the interval from here to here. From 1 to 4, how long is it? Okay, well, you just subtract these numbers to figure out how long this green segment is that I drew. So it's 3. You do 4 minus 1, so you get 3. So the length of the green segment is 3. But then I want to cut into 3 pieces. Maybe I should shade the part of the x-axis, right? So we have this one piece here, this piece here, and this piece here, which all, of course, have the same width. So you just take the length of the whole thing, which was 3, and divide by how many intervals that we're using. And here we're using 3 intervals. So you do 3 divided by 3, and you get 1. The width of each subinterval is called delta x. So delta x, basically, you did the 4 minus 1, and then you divide by how many intervals we have, which is 3. Okay, so you do this number minus this number, and then divide by how many intervals you have, and you end up getting 1. That means the length of each of these, the red segment, the blue segment, and the purple segment, the length of each is 1. Well, if the first number, the first tick mark is 1, where's the second tick mark? The distance of this red segment, the length of this red segment is 1. So if this number is 1, you have to add 1. And so you get the number 2 over here. Well, the length of the blue segment is also 1. So you add 1 again. It's like we're stepping over by 1. We get to 3. And the length of the purple segment is 1. So from the number 3 on the x-axis, if you were to take another step of length 1, you'd get to the number 4. So those tick marks are at 1, 2, 3, and 4. And again, I'm sure you knew that already, but again, if we get a more complicated number, that's what you do. So like, for example, if delta x was like, 0.2, then you keep adding 0.2 every time. Add 0.2, add another 0.2 until you finally got to the last one. Okay, let me do some erasing here. And so, okay, so first thing we did, what did we do? We had the interval from 1 to 4, and we cut into 3 pieces. Now you might be asking yourself, why 3 pieces? Hold off on that question for now. But let's just cut into 3 pieces and see what happens. So I've cut the interval from 1 to 4 into 3 pieces. I do have 4 numbers written down. Okay. Let's talk a little bit of notation before we go on. So these numbers, each of these numbers that are on the x-axis, on the number line, have a notation. The first one, we're going to call that A, and it's also called x0. Okay, the reason why we call it A is because the first number in the interval, we always call it A. The last number, we call it B. So this last one is B, okay? But the reason why I also like to call it x0 is because I don't want to use different letters of the alphabet. What if I have 50 numbers? The alphabet only has 26 numbers, 26 letters. So instead, I'd rather use x0. Then this one's going to be called x1. This one's going to be called x2. And this one will be called x3. Okay, so the numbers on the number line are... Sorry, this one's messy. x0, x1, x2, and x3. But it just so happens the first one, it could also be called A. The last one also could be called B. But x0, x1, x2, x3 is probably a little bit easier. Maybe it'll look better if I put x0 and x3 first. x0, but it just happens to be A, and x3, which happens to be B. Okay, so I want you to notice that we cut into 3 intervals, but we have 4 numbers on the number line. 3 intervals, and the last one was x3. That's probably a good way to remember it. So if we cut it into 8 intervals later, the last one's going to be x8. It always starts at x0, and the last one, the number you see, the last subscript you see on the x, will be how many intervals we used. Okay, so that's some notation. And all I've done is cut the interval into pieces. The next thing you do is you got to pick a number in each subinterval. So from 1 to 2, you got to pick a number, any number you want, but pick some number between 1 and 2. You could pick 1, you could pick 2, or you could pick something in between, like 1 point something, anything you want. So what I'm going to do for this example is I'm going to pick the number right in the middle. It doesn't have to be right in the middle, any number you want, but just I got to pick something. So I'm going to pick the number 1.5. In each interval, you have to pick a number. So in this interval, we got to pick a number as well. And in this interval, I got to pick a number as well. So you're going to be picking 3 numbers, any numbers you want. So for the second interval, I got to pick a number between 2 and 3. It could be 2, it could be 3, or any number in the middle. Just for fun, I'm going to pick the number 2.1. And for the last interval, again, I have to pick, for the last subinterval, sorry, I'm going to pick a number between 3 and 4, any number I want. And again, you could pick 3 or 4 or anything in the middle. And so I'm going to pick 3.6, which is maybe somewhere right here. Okay, so that's the second thing. So basically there's 3 things you got to do. First thing you do, cut the interval into subintervals, and in this case I cut into 3 subintervals. Then you pick a number in each subinterval. Before I go on, there's a notation for the numbers in the subinterval. Because 1.5 is in the first subinterval, the notation for it's going to be x1 star. Don't let the stars scare you. I can't call it x1 because this number here is called x1. So the number in the first interval that you just picked, we'll put a star next to it. So the number you pick in the interval, we'll put a star. So x1 star is the number you picked in the first interval. So the number we picked in the second interval, what do you think it's going to be called? x2 star. For that one. The one in the third interval, we're going to call that number x3 star. Okay, so I know there's a lot of numbers going on here. Let me just say it one more time. You first divide the interval they give you into subintervals, and in this case we divided into 3 subintervals. And I figured out what the numbers were for each of these tick marks, 1, 2, 3, and 4. And then in each subinterval, which we had 3 subintervals, we picked a number in each one. The notation for the tick marks are x0, x1, x2, up to the last one. Since we use 3 intervals, the last one's x3. And then also since we use 3 subintervals, we're going to be looking for 3 numbers, 1 number in each. And the notation for those is going to be x1 star, x2 star, x3 star. There isn't going to be an x0 star because there's 3 subintervals. We're going to have 3 of them. But even though there's 3 subintervals, we have 4 tick marks. That's why we had to have an x0. Okay, and then you build a sum, and it's called a Riemann sum. Okay, here's how that goes. So the way the sum's going to work is you're going to plug in the first number into the function. So 1.5, we're going to plug it into the function. Remember I said it's like an input, so you can plug it into the function? So we're going to calculate f of 1.5. Just means plug in 1.5 into the function. And then we're going to multiply it by the length of the first subinterval. So the length of this interval, how long is it? What is delta x? We already calculated it, but just to remind you, if you want to find the length, you can just subtract the numbers. So I just subtract the 1 and the 2. You're supposed to do the right one minus the left one. 2 minus 1. So the length is 1. So it's going to be f of 1.5 and then times 1. And you do that for every subinterval. So now we'll go to the next subinterval. And again, what are we going to do? We're going to plug in 2.1 into the function, our x2 star. So f of 2.1. We're going to plug 2.1 into the function, and we're going to multiply by the length of that subinterval. How long is it? It's 1. In this problem, it's 1. Okay? Now we'll go to the third subinterval, this one here. Same thing. You're going to plug in the number you picked. In this case, we picked 3.6. Plug that into the function, then multiply by the width of the interval, of the subinterval. So it's going to be f of 3.6. So you plug in 3.6 to the function, then you multiply by the length of the interval, which is 1. Okay, so let's one more time. All the numbers that you picked in each interval, you plug each one into the function and multiply by the width of that subinterval. The widths are all going to be the same, so in this case we're multiplying each one by 1. It's not always going to be 1, it's whatever the width of your interval is, but it is going to be the same number, so these 3 numbers will always be the same number, but it might not always be 1, it could be all sorts of numbers. And then after you do that little process there, you add them all. That's called a Riemann sum right there. Okay, so for example, in this example here, if you want to calculate it, what's f of 1.5? Well, f is x squared, So you're supposed to square whatever you plug in. So f of 1.5 is 1.5 squared. Now it's not always 1.5 squared. It's 1.5 squared because our function is x squared. If the function was sine, then this would be sine of 1.5. So it depends on whatever the function is. Plug 1.5 into the function. Okay, times 1 plus what's f of 2.1? You got to plug in 2.1 to the function here. So you're going to get 2.1 squared times 1 plus, then you got to plug in 3.6 to the function, and you get 3.6 squared times 1. And when you're done, the answer to this Riemann sum, 19.62. And that is a Riemann sum. Okay, the point is, it's a weird kind of sum, but it's important. This kind of sum shows up a lot, so we have to really understand how to calculate it. So let me just go over the whole thing one more time. So what did we do? We started off by taking the interval they gave us, which is that interval, and we cut it into pieces. How many pieces? In this problem, we cut into 3 pieces. So here's the whole interval. We cut it into this piece here, and then separately this piece here, and this piece here. 3 equal width subintervals. And since we did 3 subintervals, each one had width 1. Then you pick a number in each subinterval. In this case, we picked 1.5. In this one, we picked 2.1. In the second subinterval, we picked 3.6 in the third one. But you can pick any numbers you want. And then you calculate a sum where you plug in each of the numbers you just picked into the function and multiply by the width of that subinterval. So you do f of this number times the width of that interval plus f of this number times the width of that interval plus f of this number times the width of that interval. You add them all up, and whatever you get, that's called a Riemann sum. If I wanted to generalize this, I know I have it with numbers here, but if I wanted to write some kind of formula, it would go like this. In other words, what I'm trying to do now is I'm going to write what I just wrote again, but instead of putting numbers, I'm going to put the symbols, the notation. So we'll leave the answer for the Riemann sum, but this would be the notation for it. So what did we do? We plugged in x1 star, right? 1.5 was x1 star, so it's f of x1 star times the width of the interval, which is delta x, plus, then we plugged in x2 star into the function. So that's f of x2 star times the width of the interval, which is also delta x, plus, then we did the same thing here. We plugged in, instead of me writing 3.6, I'm going to write x3 star. So it's f of x3 star delta x. So we calculated a sum like that. So again, it's the number you picked in the interval, plug it into the function, and then multiply by the width of the interval. Do that for each of your 3 intervals, and then add them up. And that's a Riemann sum, and we ended up getting this 19.62, which will have a meaning later on. Okay, let's do that one more time. I want to do the whole thing over. I'm going to cut into a different amount of intervals this time. And again, let's practice notation and all that stuff. So same function here, same interval, 1 to 4. So this number here is 1, this number here is 4. Let's go ahead and cut it into 5 intervals. I might as well mention it now. We're going to use the letter n, a lowercase n, for how many intervals we're going to use. So in the last problem, n was 3. And in this problem, let's make n 5. Okay, so that just stands for how many intervals we're going to use, how many subintervals we're going to use. So I'm going to cut the interval from 1 to 4 into 5 pieces. To cut into 5 pieces, you're going to have 6 tick marks total. You always need 1 more tick mark than the number of pieces you want. And since there's already 2 tick marks for the 1 to 4, I have to put 4 other ones. And again, you try to make them evenly spaced. Well, close enough anyway. Those are not perfectly evenly spaced, but somewhat close. But I want you to notice I have 5 intervals now. 1, 2, 3, 4, 5 subintervals. Well, how many tick marks do I have? 1, 2, 3, 4, 5, 6. And if you don't count the end ones, because we already had them there, then you had to put 4 more. Okay. So now that I know where the tick marks are, well, actually, now that I put the tick marks down, I want to write down where they are. What are the numbers? You know each of those tick marks are at numbers between 1 and 4, but what exactly are the numbers? So the way you do it is you figure out delta x. Delta x, remember what you do 4 minus 1. 4 minus 1 gives me the length of the whole thing. And then you divide by how many intervals you want. In this case, we have 5. So it's 3 over 5, which is 0.6. That means the length of this one is 0.6. The length of this one, 0.6. The length of each one, 0.6. Makes sense. If you add 0.65 times, you're going to get 3, which is what you need because the whole distance has to be 3 here. Okay, so if this first number is 1, what's the next one? We just have to add the 0.6. Think of it as walking. You're at the number 1 on the number line. You're going to walk 0.6 to the right. What number do you end up at? You end up at 1.6. Then you're going to add another 0.6. You just keep adding your delta x's. Oops. Keep adding your delta x's to the last place you're at. Think of it as a step size, and keep doing it until you get to the end, to the 4. So 2.2, we'll add the 0.6. It's going to get me to 2.8. We'll add the 0.6 again, gets me to 3.2. And if you add the 0.6 again, you get to the 4. Okay, so that's how that goes. If you can come up with it without doing all the crazy calculations that I'm doing here, they're not even that crazy, but anyway, it's totally fine. But otherwise, I'm just saying figure out where all these tick marks are that you put. So we have 6 tick marks. Figure out where they all are. What are the numbers where you put these tick marks? Okay, so that delta x way is the way to do it. All right, so now that we know that, what we're going to do, actually, let's write some notation first. So the notation is x0. So each of these numbers where the tick marks are have a notation. This is x0, x1, x2, x3, x4, and x5. Okay, remember, the first one's always going to be called x0. The last one's x5, and you can remember that by, well, we're doing 5 intervals, so the last one will be x5. So think of it as there's x1, x2, x3, x4, x5, and then you forgot to count the x0. So we're actually going to have 6 tick marks there. Also, you can remember that the first number in the interval is called A and the last number is called B. So this x0 is also A, and this x5 is also B. Okay. To save room, I think I'll erase that though, but just you can go ahead and just remember that. Or actually, I could just put it here. So this is equal to B, and this one's equal to A. Okay, but anyway, x0, x1, x2, x3, x4, x5. So you first divided your interval into 5 subintervals. The second thing you do is you pick a number in each subinterval. Any number you want. So for the first subinterval, I'm going to go ahead and pick the number 1. You could pick any number between 1 and 1.6. You could pick 1, you could pick 1.6, or you could pick any number in between. So I'm going to go ahead and pick 1.6 for that one. I feel like this is going to get really sloppy, so I'm going to put the 1.6 on top here. Oh, sorry. Sorry, that's not the number 1.6. We picked the number 1. Okay, for the second interval, I'm going to go ahead and pick the number 2.1, which is somewhere around here. Okay, for the third interval, again, I'm going to pick, you can pick any number you want between 2.2 and 2.8. I'm going to go ahead and pick 2.8. Don't be afraid. You could use the endpoints if you want, or it could be any number in between. For the next interval, from 2.8 to 3.2, I'm going to pick the number 3.1. Remember, you can pick any number you want, so I'm just going to pick 3.1. Oh, I forgot to write that this one is 2.8. And then between 3.2 and 4, again, any number I want, I'm going to go ahead and pick 3.5. I just realized I have a little typo here. You probably already caught it, but I was supposed to keep adding 0.6, so 1.6, 2.2, 2.8. The next one should be 3.4. Okay, anyway, and 3.5 is still in there, so that's good. Okay, let's go over the notation for these 5. And remember, there's 5 intervals, so I have 5 red dots here. And the notation for the numbers that you pick in the intervals, there was a notation, that was the one with the star. So what's the notation for the 1? It's x1 star. For the numbers that you pick in the interval, don't have one that has a 0 in it, because we have 5 intervals, so we're going to have an x1 star, x2 star, up to x5 star. So we're going to have 5 of them. This one is x2 star. That's the number we picked in the second interval. The number we picked that's in the third interval, x3 star. If we had an 8th interval, what would the notation be for the number we're picking? x8 star. Okay, anyway, the next one is x4 star. That number's in the 4th interval, and the last one is x5 star. Okay, and then we're ready to build the sum. So the Riemann sum, the way that's going to work is, remember, you're going to plug in the number you picked from the first interval, multiply by the width of the interval. Then plug in the number you picked from the second interval, multiply by the width of the second interval, and do that all the way across, and then add them all. So we're going to do f of 1, that was the first number we picked, and then we're going to multiply by the width of the interval. Okay, so you multiply by the width of the interval. The width of the interval was 0.6. Plus, then you plug in 2.1, because that was your second number you picked, and then multiply by the width of the second interval, which is again 1. Oh no, it's not 1. Sorry, too many mistakes. The width of all the intervals is 0.6. Then you plug in the third number you picked, the number from the third interval, which was 2.8. And then you multiply by the width of the third interval, which was 0.6. Then plug in the fourth one to the function, 3.1, times the width of the interval, 0.6. And then you plug in the last one, f of 3.5, times 0.6. Okay, so one more time. You plug in each number that you picked from each interval into the function, multiply by the width of the interval, and then add them all. So remember, the function in this problem is x squared. But a different function, things would be different. But what does it mean when you plug into x squared? You just square the thing you're plugging in. So the first term is going to be 1 squared times 0.6. What's f of 2.1? That's going to be 2.1 squared. Again, try not to think that, oh, it's always squared. It's not. It's squared because in this example, the function is x squared. If the function was x cubed, that would say 2.1 cubed. Whatever the function is. Okay, next one, 2.8 cubed times 0.6. Next, way too many mistakes. Sorry, that's 2.8 squared. Remember, the function's x squared. So you square each of these numbers, multiply by 0.6. Next one is 3.1 squared times 0.6. And then the last one, 3.5 squared times 0.6. Okay, so that's a Riemann sum. And if you're dying to know the answer, when you calculate that one, you get 21.066. So that is a Riemann sum. It's a weird kind of sum that shows up in a lot of things we need to calculate in calculus. Okay, so one last time, let me summarize this. I shouldn't say one last time. We'll summarize it a few more times. But you take the interval they give you and cut it into subintervals of equal width. So each one should have the same width. In this case, we decided to cut into 5 equal width subintervals. Then figure out where all your tick marks are. And then after you do that, so then you pick a number in each subinterval. So that means we picked 5 numbers. In this case, the 1, the 2.1, 2.8, 3.1, and 3.5. And you plug in each one into the function, and then multiply by the width of the interval, and then you add them all. And don't forget that those numbers are called x1 star, x2 star, up to x5 star. Okay, so if we had 20 intervals, there would be an x1 star for the first interval, x2 star for the second interval, all the way up to x20 star for the last one. There would be no zero. Okay, let's go ahead and write down a more general formula for what's happening here. So again, what I'm going to do is I'm going to erase the numbers now and just use notation. I'll keep the answer, but using the x1 star, you know, and the delta x and all that, how would you write out what we just did? So what we did is we plugged in x1 star to the function. So that would be written as f of x1 star. That means take x1 star, plug it into the function. Then you multiply by the width of the interval, delta x. And then you plug in the second number you picked, which was called x2 star, f of x2 star, and then multiply by the width of the interval. Then f of x3 star times delta x plus, and it's a sum, so you keep adding. So f of x4 star delta x plus f of x5 star delta x. Okay, so that's the notation if I don't put any numbers in there. Okay, and now I want to show you something else before we go on to the next slide. You notice how it's starting to get kind of long. There's an actual compact, shorter way of writing what we have written here. I mean, take a look at the terms that we're adding. Every term looks about the same. The only difference is you see a 1, and then it changes to a 2, then a 3, then a 4, then a 5. But every other symbol is the same. There's F, there's two parentheses, there's a star, there's X, there's a delta X. Everything is the same. Just one thing is changing, and it's going 1, 2, 3, 4, 5. Everything else is the same. So what you do to write this compact notation is whatever the thing is that's changing. See, something changed to 1, then something changed to 2, then something changed to 3, then something changed to 4, then something changed to 5. What you do is you write down just one of the terms, but that thing that's changing, you put an I. You don't have to put the letter I, but you put some letter. Usual letters are I or K, J sometimes, but in this video we're going to be using I. The actual letter used doesn't matter, so look what I'm going to do. I'm just going to write down one term, but instead of putting a 1, 2, 3 or whatever, I'm going to put an I down here, because the I is the thing that's changing. See, everything else is exactly the same, just the I, where the I is changes, has to change to 1, 2, 3, 4, 5. So then what you do is you put this symbol in the front. This is called sigma. Some people will call this summation. It means add. This symbol means add. So we have to add a bunch of these things. And on the bottom you write down I equals 1 to 5. So basically what that means is you start off by changing every I you see here, which basically this is the only one you see. You first change it to 1. So if you change every I in this expression to 1, what do you get? It would be f of x1 star times delta x, and you'd get that. Then you increase it by 1. So now you change every I you see in this expression here to 2. And again, this is the only I you see, so it would become f of x2 star delta x. That would be this term. Then you increase it to 3. So again, every I you see here, we only see 1, this little one here, you would change it to 3, and then you just read the whole thing. You would say f of x3 star delta x. That's this one. Then you change it to 4. When do you stop? When you get to 5. So you start at 1, change it to 1, and then you have to increase it by 1 every time. So you always increase it by 1, no matter what the problem is. So you always go by a whole number. So you start at 1. So you start at whatever number is here, but in this video it's always going to be a 1, and then you keep increasing by 1 every time. So you plug in 1 for I, plug in 2 for I, plug in 3 for I, plug in 4 for I, plug in 5 for I, and then stop because you got to 5 into this expression, and then add them all. So this is a compact way of writing this exact same thing. Maybe we should practice that one more time before we go on to the next thing. Okay, so let me just go ahead and write down the one from the previous example we didn't do at the time. So in the previous example, if you want to write down that notation for the Riemann sum, the long way was f of x1 star delta x plus f of x2 star delta x plus f of x3 star delta x. We had stopped at 3 because in the last example we had 3 intervals. So what's the compact way of writing this? Again, take a look at this sum. Notice that every term looks exactly the same, except one part of it is changing. It's a 1, then a 2, then a 3. So what you do is you write down f of xi star. So wherever you see the thing that's changing, change it to I. Put the sum symbol in the front since we're adding. And you're going to go I equals, what's the first thing we want to change the I to? We want to change it to 1. What's the last thing you want to change the I to? To 3. Okay, and that's the compact way of writing this long thing. So here's this long thing with 3 terms, and here's the compact way of writing it. And again, what does this mean? It means, first, every I that you see here, which again is just going to be here for us, change it to 1. And it's going to say f of x1 star delta x, which is this term. Then you increase it by 1, so you'd go to 2 now. So this I would change to 2, and you change every I you see here to 2. It would just say f of x2 star delta x. You'd get this term. Then you increase it by 1 to 3, and you won't go any further because 3 is the last one here. Change the I to 3, and you get f of x3 star delta x, which is this term. And then this symbol here means, okay, now add all those terms. All right, so hopefully it's making some sense what a Riemann sum is, and some notation, and then this nice compact way of writing it. Let me go talk about this in the most general situation here. So now I'm not giving you a function. Instead of me writing x squared, I'm just writing f of x. Instead of me giving you a specific interval like 1 to 4, I'm just saying the interval is from a to b. And I'm going to mention this, and people might argue with me, but I'll sort out, if there's any little argument at all, I'll sort it out at the very end of the video. But let me just say, until I say otherwise, the first number in the interval has to always be less than the second number. Okay, so a needs to be less than b. At minimum, for this video, let's make a less than b, so that the a would go on the left side and the b would go on the right side. Okay? You might say, well, wait a minute, we're allowed to have it in the other way when you do definite integrals. And I'll try to sort that out later. Okay, so what do you do? To build a Riemann sum, what do? You divide this into intervals. How many intervals? Well, we're going to use the letter n, so you divide into n intervals. If I'm not going to specify the n here, then it's kind of hard to write it down. Let me just go ahead and write down. So let's pretend that's just we cut into a whole bunch of intervals. Okay, and the dot, dot, dot just means, you're not telling me, is it 5 intervals or 80 intervals? You're not telling me. So I'm just leave the middle kind of open like that. Also remember the first number is also called x0. So I like the x0 better. Let me go ahead and just write the a over here. So those are the same. The last one, since we have n intervals, it's going to be xn. So don't forget that. 8 intervals, the last one's x8. 12 intervals, the last one's x12. If it's n intervals, then the last one's going to be xn. The second one's going to be x1, x2, x3. So it's x0, x1, x2, x3, dot, dot, dot. This would be, well, if this is xn, the previous one, the subscript's going to be 1 less. So you might see an xn minus 1 like that. So I'm just trying to say the subscript is 1 less. So if this was x30, this is x29. This would be x28. I guess it would be x with the subscript n minus 2. Okay? Okay, so you divide the interval that they give you, a to b, into equal width subintervals. And then you pick a number in each interval. And I'm not going to make any of them endpoints because it starts to get sloppy. So I'm just going to put some number somewhere in there. So that's x1 star. That's the number we pick in the first interval. The number we pick in the second one is x2 star. Number we pick in the third interval, it doesn't matter. Anywhere in the interval, x3 star, dot, dot, dot. The very last one would be xn star. And I suppose that the one before that one, the interval before that, the number you're going to pick in there, the number you pick in there would be xn minus 1 star. So for example, again, if you have like 30 intervals, this is x30 star. This is x29 star. And one thing to remember, if you're trying to figure out, which letter goes with one, x3 star, you should be thinking, oh, 3, third interval. But if you're thinking what the endpoints of the interval are, that's the part that's a little bit confusing. Just remember that the number matches the right endpoint, okay? So x3 star is in the interval where the right endpoint is x3. That means the left endpoint, of course, is one less, so x2. Yeah. Okay. So after you cut the interval into subintervals of equal width, so n subintervals of equal width, pick a number in each subinterval. Then what you do again is you plug the numbers you picked in each interval into the function and multiply by the width of the interval of the subinterval. Do that for each subinterval and then add them up. So the Riemann sum, it's going to be f of x1 star delta x plus f of x2 star delta x plus f of x3 star delta x, and it would keep going. And I'll just write my sum like this because, again, we don't know how many terms we have. And then the second to last one would be f of xn minus 1 star delta x plus f of xn star delta x. Yeah, that's how that Riemann sum would go. And so that's a Riemann sum. And again, this kind of sum, doing it using this process, is important in some way, which we'll see later on in some other video. Okay, and let me go ahead and write down the compact notation for it. Again, just notice that every term, just the little subscript on the x is changing. Nothing else is changing. So again, the way you write the compact notation is whatever's changing, put an I instead. So this is xi star, f of xi star delta x. And then just say you want to change the I to 1, then to 2, then to 3, and keep going all the way up to the last one, which is n. And then you want to add them all. So it's going to be sum I equals 1. What's the last one going to be? If it was 5 subintervals, you'd put a 5, but since it's n subintervals, you put an n there. Okay, so this symbol, or this notation here, formula, whatever you want to call it, is the formula for a Riemann sum, and it's the compact version, and it's just the most general formula. All right, so that's how that goes. So hopefully you guys understand now what a Riemann sum is. And so before we go on to the next part, I have a little quiz to give you. Now, what you can do for fun is, for every question, before I answer it, pause the video for a few seconds and see if you can answer it. Just to test to make sure that we have notation making sense here. So let's go ahead and go with this quiz. Okay, so in this quiz, I'm going to assume for all the problems that we have a function f. The interval is ab. And we're trying to build a Riemann sum, and we've divided this interval ab into 20 subintervals. Okay, so those are the things that are given. Function f, interval ab. And we're going to build a Riemann sum by cutting that interval into 20 subintervals. All right, so here's a few questions. First question, what's the value of n? Okay, so to figure out the value of n, you have to know what n means. N is how many subintervals you're going to have. So it's not too hard. The value of n is 20. Story's over on that one. All right, let's try the next question. What is the notation for the endpoints of the 7th subinterval? The reason I mentioned that we have 20 subintervals here is because, for example, if we only had like 5 subintervals, there would be no 7th subinterval. This question wouldn't make sense. So what is the notation for the endpoints of the 7th subinterval? So I'm thinking number line, the first one's x0, x1, right? This is the first subinterval, right? First one. And then the endpoints are x0 and x1. For the second one, it's x1 and x2. Can you figure out what it is for the 7th one? Let's say this was the 7th, and I know it keeps going. So for the 7th one, what is it? And just remember that the number on the right endpoint is going to match the interval. So if we're talking about the seventh interval, this number is x7. You can see how second interval, x2. First interval, x1. The next one, the third interval, would have been, the tick mark here would have been x3. Seventh interval, this is x7, and then the one before it then has to be x6. So the answer to the question is x6 and x7. So I want you to be able to figure that out without a picture. But I drew the picture just, if you're confused at all, maybe it helped you a little bit. So to answer this question, left endpoint and then right endpoint. So the right endpoint is x7. That means the left endpoint is x6. Okay, next question. What is the notation for the number in the seventh subinterval that we will select and plug into the function? So once you have the seventh subinterval and you have your endpoints there, you're supposed to plug in some number in that interval to the function. What's the notation for that? So I would like you to be able to answer the question right away, but let me go ahead and draw this picture again. So the seventh subinterval, the endpoint here was x6, and then we have x7 here for the right endpoint. But again, you're going to pick some number inside, and what is that called? x7 star. Again, because it's the seventh interval, x7 star. Or you can, again, just remember all these numbers kind of match here. Okay, 7 star. So that's it, x7 star. That's the number. Okay, so the answer to this question, x7 star. Yeah. Now, those two questions were pretty important, so I'm going to ask you those, or similar ones to those, a couple more times during this quiz. But let's keep going. What is the first subinterval? I mean, write it as an interval. So we have this notation here for an interval. But the first subinterval, if I want to write the first subinterval like this, what would it be? So, I'm going to write it like this. What would go in there? Well, the first one's always x0. The next one is x1. That's the first subinterval. You can also put a here instead, but I'm not going to put the a there. First subinterval, the left endpoint is x0, the right endpoint is x1. Yeah, that's it. And you write it as an interval if they say, what is the interval? What is the first subinterval? Okay, next question. What is the last subinterval? Okay, well, because they said that we have 20 subintervals, the very last one, the right endpoint would be x20. Well, then this one would be x19. Yeah, that's the end of that story on that one. The last subinterval is x19, x20. Now, just to make it more general, what if it didn't say 20? What if it said n subintervals? So they just use n. Then what would it be? Well, the last endpoint would be xn. So the previous one would be x, and you just have to minus 1 on that subscript because 1 less, right? If it's 20 here, it's 19 here. So you'd go 1 less like that. Okay, next question. This is not exactly a question, but what does it say? List the endpoints, there's a typo there, of all the intervals, and then list the intervals. Well, it's going to take a little time to list them all, so I think I'll just put some dots, but it'd be, here are the endpoints, x0, then x1, then x2. These are not the numbers in the interval we pick. It's just like the ends of the intervals. x0, x1, x2, x3, x4. We'd have to keep going until x20, since we have 20 intervals. So those are the endpoints. And if you want to write down the intervals, then you just write it like this. x0, x1 is the first interval. x1, x2 is the second interval. x2, x3 is the third interval. So we have those. And let me just go to the last one, which would be x19, x20. And the dot, 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 you get the idea. The next one would be x3, x4, next one x4, x5, and just keeps going till x19, x20. These are the intervals. Once again, just to generalize this a little bit, if we get rid of this 20 and just make it n subintervals, then what would change? Well, the endpoints would be x0, x1, x2, x3. The very last one wouldn't be x20. It'd be xn. As far as writing all these intervals down, again, it would be x0, x1, x1, x2. But the last one wouldn't be x19, x20. The last endpoint would be xn, so the previous one would be xn minus 1. So that's how it would be if we were generalizing it to n intervals. Okay, next question. What is the notation for the endpoints of the 12th subinterval? Okay, so hopefully we're getting the hang of this now. So, I want you to memorize it. If you have to draw a picture, go ahead. But what was the notation for the endpoints of the 12th subinterval? If it's the 12th subinterval, the right endpoint, the notation is x12. That means the left one's going to be x11. Okay, so those are the notations for the endpoints there. Next question. What is the notation for the number in the interval that you pick to plug into the function? If it's the 12th subinterval, the thing we're going to pick is x12 star. Again, the way it works for the 12th subinterval, this is x11, this is going to be x12, and the number you pick in the middle, x12 star. Yeah. Okay, next question. Okay, what is the notation for the endpoints of the ith subinterval? So again, this letter I showed up again. So in the last two times I asked this kind of question, I gave you a specific number. What are the endpoints for the 7th interval or 12th interval? But if I just say ith interval, you're kind of going to give me a formula that works no matter what. Think of an I as a placeholder. You can write a formula, but then as soon as you tell me what I is, I can plug in that number for I and give you the answer. So the ith interval, okay, let me go ahead and draw a picture. If this is the ith interval, well, okay, if it was the 17th, right, this would be x17. But I'm not telling you the number 17, I'm just using the I instead. So this would be xi right here. Remember, they have to match. And this would be one less, xi minus 1. And so that's the answers there. These two are the answers, xi minus 1 and xi. But again, think of it as a placeholder. It's waiting for you to plug in a number. If now I said, what are the endpoints of the 17th interval? What you do is just plug in a 17 there. So for 17th interval, and you would plug in a 17 there, that would be x17. You'd plug a 17 there, you'd have to subtract 1, and you would get x16 there. Okay, so think of it as just like a generalization, general formula, but it's waiting for you to plug in a number so we can know which interval you're talking about. So a lot of times they'll say that's the generic interval. Like, what is the formula for the generic interval? That kind of thing. All right, next question. What is the notation for the number in the ith interval that we select and plug into the function? So again, the number you select to plug into the function has a star on it. If it was the 5th interval, it would be x5 star. If it's the ith interval, what do you think it is? Yeah, it's going to be xi star. So that's the answer. Hopefully you can get that without a picture. Otherwise, if you need a picture, ith interval, this would be xi. It's xi minus 1. And then the number you pick in there, xi. Don't forget that this and this all match. Oops, I forgot to put the star. Okay, so the number you pick between xi minus 1 and xi is going to be xi star. Okay, it says, what is the notation for the Riemann sum? Well, can we do it without drawing a picture? We've already done it with drawing a picture. So without drawing a picture, it would be like this. So remember, the first term, you plug in you would plug in x1 star to your function, multiply by delta x. Then you plug in x2 star, multiply by delta x. Let's go ahead and write a third term here. You plug in x3 star to the function, multiply by delta x, and you keep going until the very last one, which would be f of xn star times delta x. Sorry. Let's start with what the question's asking. So they mentioned 20 subintervals, so the last one would be 20, f of x 20 star delta x. That's the long version. And the compact version would be sum I equals 1 to 20 of f of xi star delta x. Okay, and again, if we want to generalize it now and get rid of this 20 intervals and just say we have n intervals, then the long way would be f of x1 star times delta x plus f of x2 star times delta x, all the way up to the last one, which wouldn't be 20. It'd be f of xn star delta x. And then what would change in our compact notation? Just the 20 up here is going to change. And we're going to have an n here. Okay, that's how the quiz went. All right, now let me just go ahead one more time and summarize so you really get what a Riemann sum is. And then we can go to the next part of the video. Okay, so summary. When calculating a Riemann sum, first don't forget that you're going to be given a function and you're going to be given an interval that the function is defined on. When I say the function is going to be defined on this interval, I mean, you know how functions can be undefined sometimes? You plug in a number and it's undefined. What I'm saying is there's no number in the interval that you can't plug into the function. It's defined no matter what you plug in. So you don't have any issues. Well, what if I pick this number? It's undefined. I can't pick that number. So, okay, so the function is defined at every number that's in the interval. Okay, that's the first thing. Okay, so then to build the Riemann sum, what do? You divide the interval that they give you into equal width subintervals. The number of subintervals is denoted by n, little n. The width of the intervals is denoted by delta x. Each one has the same width, delta x. If you list the endpoints of the interval, it's from smallest to largest, it's x0, x1, x2, x3. In the middle, so I wrote x0, x1, x2, x3, then I put dot, 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 and then I wrote some generic things, so some xi. The next one then would be xi plus 1. The previous thing would be xi minus 1. But anyway, and it keeps going. And the very last one is xn. That means the one before that is xn minus 1. You could write the one before that if you wanted, but how many do you want me to write? But it's x0, x1, x2, blah, 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 up to xn. And don't forget that the first one's also a, and the last one is also b. And then if you want to list all the subintervals, you just write them in interval notation. So list of the subintervals is x0, x1 for those two, then x1, x2 for those two, x2, x3 for those two. If you want to talk about the ones in the middle, there'd be xi minus 1 xi, xi plus 1. But anyway, dot, 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 and the very last one, xn minus 1 xn, like that. So a bunch of intervals. Then you have to pick a number in each interval. So the number you're going to pick in the first interval, x0, x1, the number you're going to pick is called x1 star. The number you're going to pick in the second interval, x1, x2, is going to be called x2 star. The number you're going to pick in the third interval, x2, x3, is going to be called x3 star. If we go to one of the generic ones, xi minus 1 xi, the number you're going to pick in that interval is xi star. Don't forget that it kind of lines up, the right endpoint subscript kind of lines up with your star subscript, which also lines up with which interval we're talking about. Oh, I see I have a typo here. That's unfortunate. I'll fix it in the next slide here. But anyway, in the interval xi to xi plus 1, the number that is selected is xi plus 1 star. If you go to the last one, xn minus 1 to xn, the number you're going to pick in that interval is xn star. Yeah, the reason I have it wrong is, okay, the number in the first interval, that's the first interval, but this is not the first. It's the second interval. This is the third. So sorry about that. Then I guess this one would be the ith. So I'm looking at the right endpoint. I see an I there. This would be the I plus first interval. And this one would be the nth interval. Okay, cool. All right, so then after you pick those numbers, then you build your Riemann sum. And the notation for the Riemann sum, the long version, you plug in x1 star to the function, multiply by the width, plug in x2 star, multiply by the width, dot, 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 all the way to the last one, plug in xn star to the function, multiply by the width, and add them all up. Or the shorthand notation where you change all the things that are changing, 1, 2, 3, 4, and so on, change it to an I. Put the sum notation, then just go from 1 to n. So there's the compact version. So this mess here is the general symbol, the general formula for a Riemann sum. Okay, so now I'm convinced you know what a Riemann sum is. If you're not, go back and watch the video again. Watch as many times as you need to. Make sure you understand the way you build a Riemann sum. By cutting an interval, picking numbers in the interval, plugging them into the function, multiply by the width, add them all. That's a Riemann sum. So at this point, you should have questions like, okay, so you had us find some Riemann sums, but why did you pick 3 intervals, 5 intervals? Why did you pick the amount of intervals you wanted? Is it going to tell me in the problem how many to use? Okay, so again, this is leading somewhere. So we're not completely done with the process yet. But we have to understand this kind of sum, this Riemann sum. What you're going to do when you're calculating a physical quantity, something like area, volume, or whatever you're calculating using this process that we're talking about, is you're not going to build just one Riemann sum. You're going to build lots of them, at least in theory. Okay, so the idea is, how many intervals are you going to use? All possible amounts of intervals. So what I'm writing down over here is I'm going back to our function x squared from 1 to 4. And we're going to build a bunch of Riemann sums. I'm going to start with 1 interval, then I'm going to do 2, so 1 subinterval, then 2 subintervals, then 3 subintervals, then 4. And you understand, like, in this way I build a list of numbers, a list of Riemann sums. Okay, so for example, again, the number of intervals is not going to be, the number of subintervals you want is not going to be specified. You're going to do it for all possible amounts. So I'm going to start off by using 1 subinterval. So that means 1 to 4. I'm not cutting it in any pieces because it's already 1 interval. But you're going to pick a number in between 1 to 4. And what I'm going to do for this first example is I'm always going to use the left endpoint of every subinterval. There's only 1 subinterval. So left endpoint is going to be this point. So that's the number I'm going to use to plug into the function. So the very first Riemann sum that I'm going to get, it's going to be f of 1 times the width of the interval, which is 3. Because again, the width of the interval, how long is this thing? You just subtract the numbers 4 minus 1, it tells you 3. So this length is 3 here. So you plug in this number to the function, multiply by 3. And that's it. We don't add because it's just one term, because we just have 1 interval. If we had 7 intervals, we'd have 7 terms to add, but we just have 1 interval. And that would be 1 squared times 3. And the answer to that is 3. Okay, so we're going to focus on only left endpoints for this example here. Okay, so when n is 1, the Riemann sum we get is 3. Okay, let's go ahead and do it for 2 intervals now. So this is a 1, this is a 4. I'm going to cut the interval into 2 intervals. What number is that? There's a couple ways to figure it out. One way to do it is figure out what your delta x is. Delta x is going to be 4 minus 1, which is the length of this whole thing, and divide by 2 since we have 2 equal pieces. So it's going to be 1.5. So that means to go from this number to this number here, you have to add 1.5. And then to go from this number to this number here, you have to add 1.5 again. You just keep moving over 1.5. Okay, so that means the number in the middle is going to be 2.5. There's other ways to figure it out too, but this way I'm showing you how to do it was going to work always. So this number is 2.5. Okay. Now I'm going to pick a number in each subinterval, and as I said, for this example, I'm going to use left endpoints. So for the first interval here, we're going to use this number. So 1 is the first number to pick. For this interval here, we're going to pick the 2.5. So we're going to get 2 terms. The first term, we're going to plug in 1 to the function and multiply by the width. What's the width of this subinterval here? Again, you could just subtract 2.5 minus 1 to get the width, and it's going to be times 1.5. Plus next term, we're going to plug in this number, 2.5, into the function and multiply by the width, which is again 1.5. It's always 1.5. Also, you could just subtract these to get the width, but it's going to be the same every time. All right, you plug in the 1, you get 1 squared times 1.5. Next one is 2.5 squared times 1.5. And when you're done calculating this, you get 10.875. And that's what we'll put here. And we're going to keep doing this. So you do it for 1 interval, do it for 1 subinterval. Then calculate another Riemann sum for 2 subintervals, then calculate another Riemann sum for 3 subintervals, and on, and see what, and you get, and in that way, you get a list, a sequence of Riemann sums. And then you want to look at that sequence. We don't have to always use left endpoints, but just for this example, I'm using left endpoints. The truth is, you could pick random points for all of them. Use 1 subinterval, pick a random point. 2 subintervals, pick a random point. Okay. So let's go ahead and do it for 3 subintervals now. So this is 1, this is 4. 3 subintervals, I have to cut it like that, and it's going to be 2 and 3. You could probably see that pretty easily. Otherwise, you find delta x. And how do you what you want to do is you want to figure out the width of each little subinterval. So first you take the width of the whole thing, which again is 4 minus 1, because you subtract the right number here minus the left number. So that's going to be 3. And you divide by how many intervals you want. So each one gets equal share. And so you get 1. So that means to go from this number to this number, you have to add 1. To go from this number to this number, you have to add 1. To go from this number to this number, you add 1. And then so that's how we get those numbers. All right. So then we have to pick a number in each interval. And again, we're going to focus on just left endpoints for this problem. So for the first interval from 1 to 2, I'm going to pick the number 1. For the second interval from 2 to 3, I'm going to pick the number 2. For a third interval from 3 to 4, I'm going to pick the number 3. And we're going to form our Riemann sum. We're going to plug in 1 to the function, multiply by the width of the first interval, which is 1. Then we're going to plug in the second. So we plugged in the 1. Now we're going to plug in 2 to the function, multiply by the width of the interval, which is again 1. Then we're going to plug in the third number we picked, and multiply by the width of the interval, which is 1. And then you add them up. And again, because my function is x squared, f of 1 is 1 squared. So times 1 plus 2 squared times 1 plus 3 squared times 1. And when you're done calculating that, you get 14. And that will go here. Okay, so then the next question is, when do you stop? Well, the answer is you're never actually going to do it this way. This is just so you get the idea. I want you to understand the process. This is what definite integrals are doing. Okay, so let's go back one more time. So we know what a Riemann sum is, but it depends on how many subintervals you have. So if I give you a function and an interval and you want to calculate a Riemann sum, if I give you a function and an interval and I want you to calculate a definite integral, what's happening is you take the interval, cut it into one piece, build a Riemann sum. Then cut it into 2 subintervals, find another Riemann sum. Do 3 subintervals, another Riemann sum, and keep going. 4 intervals, Riemann sum, 5 intervals, Riemann sum, all the way down. And in that way you get a sequence of Riemann sums, the whole sequence of numbers. So I did it for up to 10 subintervals, each time using the left endpoints. Let me go ahead and show you the numbers that we got. At least we got this. This is a sequence here, okay? Infinite. It's a list. Sorry, it's a list of Riemann sums, but I only went up to 10. Then what you want to do is you want to take the limit. Now, if you're uncomfortable with limits, let me just say this much: it's like as you scroll down this list, where do these numbers look like they're headed? Okay, that's what a limit is. Where are these numbers headed towards? Where are they settling down to? Where are they going? Now, you might make a guess right now, but actually it's not easy to make a guess right now because we only did 10 subintervals. So what I did is I went on Excel and I had Excel calculate more than 10 subintervals for me because, you know, when you want to do many subintervals, you don't want to do it by hand. But the idea is you keep going past 10. So ... After 100, let me show you what happened. Again, on the other side, think of it as a, going on, keeps going on. The 100th one ends up being 20.77 something. So you still might say, okay, let's see. The number started at 3. We did one interval, then 10, then 14. And now it looks like, okay, 18, 19, 20. Okay, you might still make a guess where it's headed, but maybe it's still not enough. So I said, okay, Excel, do more for me. So we want to keep going. So you keep going. I had Excel go to 1,000. So it cut this interval into 1,000 pieces of equal width. Each subinterval, we plugged in a number to the function, multiplied by the width, and then added them all. And the number we picked was the left endpoint in this example for each interval. And this is the number we got after 1,000 intervals. And again, that's not enough to... okay, how many do you see there? There's only 12 results there. But it's really an infinite list of Riemann sums. So this list of Riemann sums goes on forever. They call that a sequence. So it's a sequence of Riemann sums. I want to know what's the limit of the sequence. Where are these numbers headed? So you want to keep going. So you want to go on and on and on. Where are we going? I don't want to put an infinity here, so I'm going to erase it right after I put it. Because if I put an infinity there, it's kind of like at infinity, what's the answer? Like at 9, here's the answer. At 6, here's the answer. What is it at infinity? We're never going to know what it is at infinity. We can never get to infinity. That's why it's a limit. If we head towards infinity, where do these numbers head towards? So let's get rid of that infinity right away. Where does it look like the Riemann sums head to? And you could probably make the guess now after 1,000. You're probably like, oh, after 1,000, we're probably pretty close. So what would your guess be? I'm sure most of you are thinking 21. So that's our guess for the limit of the Riemann sums. Okay, so remember, a Riemann sum can be calculated once you've taken your interval and cut into subintervals. So when the question arises, well, how many subintervals do we use? The answer is you're going to use 1, get an answer, then use 2, get an answer, then 3, get an answer, and do this forever. You know, after you get to 1,000,000, then you do 1,000,001, then you do 1,000,002 subintervals, and each time you get another Riemann sum, and it gives you a sequence of Riemann sums. And what the definite integral does for you is it tells you what's the limit of this sequence of Riemann sums. And in this example here, it looks like the limit is 21. Before I go on to the next couple of examples, I want you to get a little idea of why we're doing this now. So what's going to happen is you're going to be calculating something. Let's just say area, for example. You want to find the area of something. What you're going to do is, because you need calculus to find the area, what you do is you start off by making an approximation. So what you do is you cut the interval they give you into one interval, and let's say this is an approximation for the area. Now again, it doesn't have to be area, it could be any quantity, volume, surface area, arc length, work, whatever it is. But this 3 is an approximation to what you're trying to calculate. But it's a bad approximation because we only used one interval. So then the idea is you go use more and more intervals. So you use 2 intervals and now you get this approximation. Then use 3 intervals, you get this approximation to what you're trying to calculate. And as you go down, you get better and better approximations, none of which are correct, but they get better and better. And so the idea is, you know, as the number of intervals heads to infinity, not gets to infinity, but heads to infinity, where does that Riemann sum sequence look like it's headed towards? And what it's headed towards is the actual answer to what you're trying to figure out. So again, the limit, it's a limit of Riemann sums. These are Riemann sums. It's a limit of Riemann sums. That's what a definite integral is. It's a limit of Riemann sums. Each Riemann sum is a better and better approximation to what you're trying to calculate. So when you take the limit, you get the actual answer to the thing you're trying to calculate. So that's what's happening there. Okay, so now what I'm going to show you, so hopefully you get this idea of what a definite integral is, what a limit of a sequence of Riemann sums means. But here's the thing. I want to show you, I keep telling you, you can use any point in the interval you want. Okay, so what I'm going to do is I want to show you just a couple more examples real quick to show you if I would have used different endpoints or different points in the interval, I'd get the same answer for the limit of this sequence of Riemann sums. So this answer here, our guess was 21. So let's do the problem over. This time we're going to use right endpoints. So again, the first Riemann sum, the way it's going to work, this is the number 1, this is the number 4. We're going to cut the interval into one subinterval. That means we're not going to cut it into anything at all. Then we're going to use the right endpoint this time. So from 1 to 4, I have to pick a number between 1 and 4. It could be 1, it could be 4. We're going to pick the right endpoint. We're going to pick 4. So the Riemann sum you get is f of 4, because you got to plug in the number you picked, times the width of the interval, which is 3. Again, I'm getting the 3 by 4 minus 1. And so, okay, f of 4, remember we're plugging into this function, same function, so it's 4 squared times 3. When you're done with that, you get 48. Okay, let's go ahead and cut into 2 intervals now. We did it earlier, so I won't go through the work again, but this is the number 2.5. Okay, so I'm going to pick a number in this interval. I'm going to pick the right endpoint this time instead of the left. So use 2.5 for that interval. For this interval here, we're going to again pick the right endpoint, so we're going to pick 4. The Riemann sum we get is f of 2.5 times the width of the interval. We had done it earlier. It was 1.5 plus, and then we're going to plug in the 4. So f of 4 times 1.5. Remember what that means? 2.5 squared times 1.5 plus 4 squared times 1.5. When you're done with that, you get 33.375. That goes here. Okay, so now we'll cut into 3 intervals. And again, we had done this before already. This was 2 and 3. For this interval, again, I got to pick a number. We're going to pick the number 2. So that's my x1 star right there, 2. My x2 star, the number in my second interval, we're going to use the number 3. My x3 star for my third interval, we're going to use the number 4. So the Riemann sum would be f of 2 times the width of the interval. Each width is 1 plus f of 3 times 1 plus f of 4 times 1. So 2 squared times 1 plus 3 squared times 1 plus 4 squared times 1. And we're done calculating that. You get 29. We're going to put that here. And on we go. So again, that's the idea, that if you're trying to figure out how many intervals you use, the answer is you do it for every possible amount of subintervals. So you do one subinterval, pick a number between, get a Riemann sum. Pick 2 intervals. Cut the interval they give you into 2 subintervals. Pick numbers in each interval and build a Riemann sum. Do it for 3 subintervals and keep going and see what this list or sequence of Riemann sums looks like it's headed towards. Okay, so we decided to use right endpoints the whole time here. I know we did the first 3 already, but then if you just go up to 10, these are the numbers you get, and you can look at those and try to guess where they're headed. And if you can't see where they're headed, I don't think it's completely clear yet, except for the fact that you know what it should be from the left endpoint example. Since it's not clear yet, what do? Keep going. So again, I had Excel keep going. It did 100 subintervals and used right endpoints for your xi stars. And this is the answer that we get, 21.22545. That's after 100 subintervals. And then I had Excel keep going. Had to go to 1,000. 1,000's not enough, you understand? We have to keep going closer towards infinity. Okay? But at some point, we're just going to make a guess. So after 1,000, this was the value for the Riemann sum. And so now I'm just asking you to make a guess. Guess the limit. Okay, so we have an infinite sequence of Riemann sums. As we go down, n, which is the number of subintervals, is getting larger and larger. And I'm asking you, where are the Riemann sums headed? So as we go down the list, when n, the number of subintervals, keeps increasing, where are the Riemann sums headed? And what would your guess be? I'm sure you can see you would have the same guess as the last one. And it looks like it's headed to 21 again. Okay, and you don't have to use left endpoints or right endpoints. You can use any endpoints you want. Let's look at another way of picking the xi stars. So I'm keeping the same functions. This time I'm going to use the midpoints for my xi stars. Midpoints. Okay, so we're going to start off by using one subinterval. So this is the number 1, this is number 4. We already have one interval, so we're not going to cut it into any more pieces. But we're going to use the midpoint for my x1 star, and the midpoint is 2.5. If you're ever trying to find a midpoint, all you have to do is take the average of the numbers on the ends. So you just take 1 and 4, you add them. So you get 5, and then you divide by 2. So you just find the average. The average will give you the number right in the middle, so you get 2.5. So then the Riemann sum would be f of 2.5, because that's the number that gets plugged into the function, times the width, which is 3. So you would get 2.5 squared times 3. And again, please let me just remind you one more time that you're not always squaring the number. But the only example we've looked at, the function was x squared. That's why we're squaring. Okay, and then you multiply by the width. So anyway, 2.5 squared times 3, and you get 18.75. And that's the number we put here. Okay, if you're going to cut into 2 intervals, this is 1, this is 4. We're cutting into 2 subintervals. That means this number is 2.5. And now I got to pick numbers in between. So the number over here, again, I'm using midpoints for this example. So the number I'm going to pick in the first interval is the midpoint between 1 and 2.5. So what is the midpoint between 1 and 2.5? So again, you have to add these. So you get 3.5 and divide by 2. And it looks like 1.75 for that one. Then for this interval over here, between 2.5 and 4, we're going to pick the midpoint again. So again, you could just take the average of those two to get the midpoint. So 2.5 plus 4, and then you divide by 2. So that's 6.5 divided by 2. $3.25. Now that I have all that set up, we can go ahead and calculate the Riemann sum. So we're going to get f of 1.75. You got to plug that into the function. Multiply by the width. Now, don't get the width confused. It's the distance from here to here. Don't look at the red dots for the width. It's where the tick marks are. Okay, so the width is going to be 1.5, like it's been. Plus, then you plug in 3.25 to the function. Then multiply by the width, 1.5. Again, f of 1.75 means plug 1.75 into this function. That means it's 1.75 squared times 1.5 plus 3.25 squared times 1.5. And when you're done calculating that, you get 20.4375. That's going to go there. So that's a Riemann sum after we do 2 subintervals. If we're going to do 3 subintervals, this is 1, this is 4, 3 subintervals. I need to put 2 tick marks here. It's going to be 2 and 3. The delta x is going to be 1. And again, we're going to be using midpoint. So for this interval, the number we're going to plug in is 1.5. For this interval, we're going to plug in 2.5 because that's the midpoint. For this interval, we're going to plug in 3.5. And so the Riemann sum is f of 1.5 times the width, which is 1 for that subinterval, plus for this subinterval, we're going to plug in 2.5 and multiply by the width, which is 1. So we did this one. We just did this one. And now we'll do this one. We're going to plug in 3.5 to the function and multiply by the width. All right, so 1.5 squared times 1 plus 2.5 squared times 1 plus 3.5 squared times 1. And when you're done with that, you get 20.75. And that number goes there. So one more time, the idea is you're going to use one subinterval, calculate a Riemann sum, in this case using midpoints. Then use 2 subintervals, calculate a Riemann sum using midpoints, 3 subintervals, and so on, and you get a sequence of Riemann sums. Remember, the idea is that each Riemann sum is an approximation to something you're trying to calculate later on, and the further you go down the list, the better your approximations are. And so we want to know where they're headed, and that where they're headed will be, which is called the limit, is the actual answer to whatever you're looking for. So after you do the first 10, these are the Riemann sums that you get, but we got to keep going. So after I have Excel do 100, you get this Riemann sum. And again, I'm just trying to go down this list and guess where these numbers are headed. If it looks like it's pretty clear here, but if you're not sure, you go more. So add Excel go to 1,000. And then it just gives 21. Basically, the answer is actually not 21. It's 20.9999. So many nines that it just rounded to 21. Okay, but I want you to know it's not exactly 21 because if you get exactly 21, you might start thinking, well, wait, maybe it's going to go past 21. It doesn't go, so it's actually a little bit less, and then you want to guess where it's headed. But anyway, so the number of subintervals you want to go to infinity, okay? So this way we're going to infinity. We're not getting to infinity, we're going to infinity. And then I want to know where do the Riemann sums look like they're headed, and our guess, 21. Notice that at least for these three examples, we kept getting the same guess. Left endpoint, right endpoint, midpoint, we kept getting the same guess. Okay, I'm going to show you one more just like this. So same function, x squared, but instead of using left endpoints or right endpoints or midpoints, I'm going to have Excel randomly pick a point in each subinterval and calculate a Riemann sum for me. So I'm using random points. Now I'm going to tell you what Excel ended up using. So one more time, we're going to start with one interval. And so the endpoints are 1 and 4, the width is 3. And what's the point that they ended up using? This is actually going to be wrong. I rounded all my answers because the numbers that Excel picked had a lot of decimals in it. But I'll just round it for the sake of this video. So 1.54 is the number that Excel decided to use. So how do you build the Riemann sum? You plug 1.54 into the function. Remember, that's x1 star. And you multiply by the width, which is 3. And again, that means you're going to plug 1.54 into the function. So it's 1.54 squared times 3. And the answer that you get when you do that, 7.160114. If you didn't get exactly this answer here, that's because this circled answer is the answer that Excel gave me. But 1.54 is actually a rounded number from what Excel gave me. Okay, so we have that. So then I had Excel cut the interval into two subintervals. One for the number in the middle here is 2.5. In the first interval between 1 and 2.5, Excel decided to pick the number 1.36. Again, this is actually a rounded number. And then for the second interval, it decided to use 2.67. So how would Riemann sum work? You'd plug in the first number into the function, multiply by the width of the interval, which is 1.5, plug in the second number, multiply by the width, which is 1.5, and again, this function squares whatever you plug into it. So this is the Riemann sum you get for two subintervals and the numbers that they picked for the xi stars. And when you're done, you get 13.46169. Again, if you don't get exactly that answer by putting this in the calculator, it's because I used a rounded number here and here, but this number assumes that this and this were the numbers Excel was using and not the rounded versions here. But anyway, that answer goes over here. And then one more time for three subintervals. So to cut into three equal width subintervals, this would be 2, this would be 3. And then the numbers in the intervals that Excel decided to use, for the first subinterval, it used 1.49. Again, that's rounded. For the second one, it used 2.85. And for the third one, it used 3.13. So the Riemann sum you get is f of 1.49 times the width of the interval plus f of the second number times the width of that interval plus f of the third number times the width of that interval. Again, plug these into the function. And when you're done calculating that, you get 20.11911. And that's going to go there. Okay, so Excel just kept doing this. Then it cut the interval 1 to 4 into 4 pieces, 4 subintervals, picked a random number from each interval, calculated Riemann sum. Then it did it for 5 subintervals and so on. After 10, this is the list we got. Already you can try to guess where the Riemann sums, the sequence of Riemann sums is headed. But let's keep going. After 100 subintervals, the number was 21.0054. After 1,000 subintervals, the answer was 20.0006. And of course, I could have done this over again. We would have got a different list of numbers. because every time it's picking a different random set of numbers to plug into the function, random set of xi stars. But anyway, we want to keep going. We want to go to infinity. We want the number of subintervals to go to infinity. And when it goes, as it's going to infinity, we want to see where is the sequence of Riemann sums headed. What is the limit of the sequence of Riemann sums? And from here, I'm sure you can guess that it's going to 21. So I thought that was pretty cool. That 4 different ways of doing it, left endpoint, right endpoint, midpoint, or just some random point, if you do enough of them, you can kind of see that sequence of Riemann sums is going to 21. So I guess I want you to see 2 things. First of all, I want you to see that the definite integral is a limit of a sequence of Riemann sums. So I want you to understand that. And I also want you to understand that in, well, basically every problem we're going to see in this class, I'll talk about a little more in a few minutes. The limit's going to be the same no matter what point you use in each interval. So you don't have to worry about what point. You just pick a point in each interval and do it. It doesn't matter which one you pick. You're going to always get the same answer for the limit anyway. Your individual Riemann sums might be different, but where they headed, they're all headed to the same number. Okay? And also don't forget that basically what a Riemann sum really is it's you approximating some quantity. Like again, if you wanted to find an arc length, this Riemann sum is an approximation to the arc length. This next one is a better approximation. This is a better one, and a better one, and a better one. And the actual arc length that you're looking for is the limit of these numbers, and it's this. Okay, and just some general picture here. Okay, so I'm not going to write too much here, but anyway. So if you have some general function here, and the interval is a to b. Okay, maybe I'll write something. So you cut into one interval, the first number you pick, x1 star, and your first Riemann sum is f of x1 star times delta x. That goes here. Okay, then you cut it into 2 intervals. So this one would be x0, x1, x2. Say the number you pick in this interval is x1 star. The number here is x2 star. And you build the corresponding Riemann sum, which is f of x1 star times delta x. Delta x is different now because I have 2 subintervals. And then f of x2 star delta x. Don't forget compact notation for that is I equals 1 to 2 of f of xi star delta x. Anyway, whatever number you get, that goes here. And on you go. You cut into 3 intervals, get a Riemann sum. 4 intervals, get a Riemann sum. And this way you get a sequence of numbers. And you want to know, as the number of subintervals goes to infinity, where are these headed to the whatever the limit is. That limit is the definite integral. Cool. So that is the process. And the video is not done, but basically we're done. I mean, that's the process. Just a couple little things to make sure I clean up, and then that's the end of the story there. So remember, last thing to remember, as far as this part of the video goes, is a definite integral. What is it? It's a limit of a sequence of Riemann sums. It's a limit of a sequence of Riemann sums. Okay. Okay, so in a nutshell, a definite integral is a limit of a sequence of Riemann sums. Remember the formula for a Riemann sum goes like this. So there's a Riemann sum. So if n is 1, remember n stands for the number of subintervals. If n is 1, then we're cutting the given interval into 1 subinterval. We get a Riemann sum. If this n is 2 now, then we're cutting the given interval into 2 subintervals. And so for every different number here, n equals 1, 2, 3, and so on, we get a different answer for this. We get a sequence of Riemann sums. I want to know where that sequence is headed. Headed when what happens? When the number n gets bigger and bigger and bigger. So we're taking the limit of this sequence. What do I mean by limit? Limit is what happens. As the number n gets bigger, what happens to the Riemann sums? So what we're really finding is the limit as n goes to infinity of the sequence of Riemann sums. Sequence of Riemann sums, it's a sequence because it depends on n, and it's a limit as n goes to infinity. We want n to get bigger and bigger, and we want to know what that number is, and whatever that number is, that is the definite integral. So that's what an integral like this will tell you. It will tell you this limit. Okay, so that's what you need to understand. Okay, so limit of a sequence of Riemann sums is a definite integral. And basically what I like to think of is, people say that this symbol looks like an elongated S, and S stands for sum. That's kind of the point. That's kind of why they use that symbol. Some other people will say, an integral is a glorified sum. But I guess the way to really think about it is that symbol there is doing two things for you. It's finding sums, and it's also taking limits. Okay, so here's the sum, but it's also taking the limit. So kind of this together is summarized in this symbol here. Okay, so that symbol is a limit of a sequence of Riemann sums. Limit of sums. Okay, so first question. So this part of the video is just some questions and comments I want to make. So the question is, when will the definite integral exist? Don't forget, a definite integral is a limit. Limits don't always exist. So when will this limit exist, and when will it not matter which point you use? Okay, so I can't give you the entire answer for when it will exist. Basically, when it exists, we have a name for when it exists. We say the function is integrable over the interval if this limit exists. But for us, we don't need to know what are all the situations where this limit will exist. What are all the situations where a definite integral will exist? What I want you to know, and the functions we're going to see in this class, basically if the function is continuous on the interval, then the limit of the Riemann sum sequence will exist, and it'll be the same no matter what point you use inside the intervals for your xi stars. Or if the function is piecewise continuous. If you don't know what continuous means, actually let me go ahead and show you the answer real quick. So when the function is continuous or piecewise continuous on the interval AB, the ones we're going to see in the class are basically going to just be continuous. So we don't even have to worry about piecewise continuous. But if it's continuous or piecewise continuous, for sure the definite integral will exist. Or another way to say it is the limit of the Riemann sums will exist. And it will exist no matter what points you use for the xi stars. So what does continuous mean? It's a long story. Let me just say this much for now. So if I have a function so the graph starts at A and ends at B, it's continuous basically if, let's say this is what you get when you plug in A and this is what you get when you plug in B. If you can draw the graph from the first red dot to the second red dot without ever taking your pen off the paper. So something like this is a continuous function. I was able to draw it the whole time without taking my pen off the paper. Okay, so f is continuous on AB. That means over the entire interval. You can draw the whole thing without taking your pen off the paper. Let me try to squeeze in an example of a function that's not continuous on AB. If the graph looks something like this, so I couldn't draw it all the way from A to B without taking my pen off the paper. You draw from A to this circle, and then you have to take your pen off and then go over here to continue. Okay, that would not be continuous, for example. But the second example is actually piecewise continuous. Piecewise continuous means it's continuous except for at specific points. So except for a couple of points, 1 point or a few points, it's going to be continuous. So this example, the only reason it's not continuous is that this one number, I don't know, let's call it C, but it's continuous from A to C. You can draw it all the way from A to C, basically without taking your pen off the paper, then from C to B without taking your pen off the paper. So that's piecewise continuous. Let me go ahead and draw a more complicated piecewise continuous function. So something like this, if it goes like this, and then there's a, open circle there, then it jumps down to here, and then who knows, goes to here, then it jumps up to here. I don't know. This is piecewise continuous. It's only not continuous at these two dots. Let's call it C and D. Okay, but otherwise it's continuous. It's continuous from A to C, C to D, D to B. So those are piecewise continuous. So let's erase this one. So basically the idea is, if you have a nice enough function, and all the functions we're going to see are probably not even going to be piecewise continuous, they're just going to be continuous. So we don't have to worry so much about that. But there are some nasty functions with nasty formulas out there, and then so there's could be some problems where the definite integral doesn't exist. But anyway, we're not going to have to worry so much about that in this class. So just get the process and you're going to be good. Okay, so the next question is, suppose you're trying to calculate some quantity, and you're setting up the problem, and you end up with this limit of a Riemann sum. Take a look at this. It's a limit. It's a limit of a Riemann sum. That's what there's a Riemann sum there. And then they give you the interval. And the question is to write this as a definite integral. So we learned about limits of Riemann sums, and you can write that as with the definite integral notation that we talked about at the beginning of the video. And the thing is, you look at this over here. First thing I guess I want you to know is, if you look at the limit of the Riemann sum part, the interval is not mentioned, so they're going to have to mention the interval somewhere else. They're going to have to give you the interval, or in the word problem, it's going to have to be obvious what the interval is, okay, because they have to give you an interval. But then when you look at the Riemann sum part, you should be able to figure out the rest of the integral part. So basically, as far as notation goes, you're going to put the integral symbol here. I mean, this is a little bit cheating, but you can kind of think, remember I said that this integral symbol is kind of like an elongated S? I've heard people say it's like a glorified sum. Here's a sum, and then there's a limit. So it's a limit of a sum. Think of everything I have here in this blue box up here. That turns into this integral symbol. Don't forget that the symbol is not a sum. It's a limit of a sequence of sums, of Riemann sums. Okay, so basically, short way of saying it is this symbol does two things for you. It takes a sum and then finds a limit. Sum and limit at the same time. Okay, takes a sum and then finds a limit of a sequence of those sums. So a limit of a sum. So this part basically that's in the box here changes to the integral symbol. Okay, then think of the delta x as turning into the dx. And then everything else, everything that's in here, that's your function. Okay, so your function goes there. Except you're not supposed to have an xi star. So wherever you see xi stars, I guess you could just think of it as change them to x's. So this would be square root of x tangent x. So instead of xi star, just put an x. And then, of course, you got to put the numbers on your interval. So the interval is from 0 to pi over 4. So put the first one on the bottom, second one on top. And that's how you would write that as a Riemann sum. So one more time. This part turns into the integral symbol. This part turns into the dx. This is the function, but instead of xi star, put x. And then put this number on the bottom of your integral sign, this one on the top. And let's do one more like that. So again, suppose you're calculating something like arc length or something, and you end up with this expression here, limit of a Riemann sum, and then you have this interval. Write the definite integral notation for this. So again, think of this part here. as the integral symbol. You can go ahead and put the 1 and 8 on there. 1 goes down there, 8 goes there. For now, let's just say you always put the smaller number on the bottom, bigger number on top. Another way to say it is the left number on the bottom, right number on the top. Because for now, I've been saying the left number has to be smaller than the right number. Then think of this as turning into the dx. And then this is the function that you put here. Just wherever you see an xi star, write x instead. So instead of xi star to the fourth, it's x to the fourth. Instead of 7xi star, it's 7x. On the bottom, it's going to be natural log of, instead of xi star squared plus 1, it's just x squared plus 1. And you see, so instead of having to go through the whole long process of cutting your interval into subintervals, looking at the sequence of Riemann sums, and taking a limit, you just have to do this integral, which fundamental theorem of calculus makes, maybe not the one I have written here, but makes most integrals really easy to find. So it's really nice to have that fundamental theorem part too, that it lets you calculate the integral so fast. But I still need you to understand, well, what's really happening? What does this number actually mean? It really means we have an infinite sequence of Riemann sums, and we're trying to find where are those numbers headed. Okay. And then just a couple of comments. First on the interval and delta x. Okay, so as I mentioned before, the interval, a to b, for the most part, this is the smaller number, and this one is the larger one. Everything I've done, assume that the first one number was smaller, second one was larger. And then we had the formula. There was a formula for delta x. It was b minus a over n. Right? Because, you know, the original interval that they give you, starting number is a, it's smaller. Second number is b, it's larger. And so the width of this whole entire interval, if you ever have numbers on a number line, you want to find how far apart they are, you subtract. You always do the right one minus the left one. For example, if I want to know how far apart the numbers 1 and 7 are, you do 7 minus 1, and you get that this length here is 6. Always do the right one minus the left one. That's why I have b minus a over n here. Well, b minus a, so the b minus a gives me the length of the whole thing. But then if you cut into a bunch of intervals, what's the width of each one? So for example, what's the width of this one? Well, if it was 10 intervals, you would do b minus a divided by 10. But since we have n intervals, this would be b minus a over n. You just divide by how many intervals you have. So that's b minus a over n, b minus a over n, b minus a over n. Each one of these widths is b minus a over n. And since you have n of them, you end up getting b minus a. That's the idea there. So that's the formula for delta x. Now, what happens if in your definite integral, the numbers are reversed? For example, someone says, okay, I want you to calculate, integral from 7 to 3 and blah, blah, blah. Some definite integral like this. Well, what changes? Well, if you want to think of the number line, 3 is still first on the number line. And you can imagine cutting it into pieces. Let's say we cut into this many pieces here. Well, the first interval then, this would be your x0 now. This would be your first interval. This would be x1, x2, this would be x3 here. The number you pick in the first interval would be x1 star. This would be the number you pick in the second interval would be x2 star. It's kind of like you're doing the Riemann sum backwards. The number you pick here is x3 star. Okay, fine. Do that, the Riemann sum. That's okay. Go backwards. What's the difference? So you're going to get, the first term would be f of x1 star delta x plus f of x2 star delta x plus f of x3 star delta x. Okay, no problem. We're just going backwards, going this way instead of going that way. But here's the deal. When I first told you what a Riemann sum was, I said you plug in a number. Okay, so we plug in a number and you multiply by the length of this interval. Then you plug in a number here, multiply by the length. Plug in a number, multiply by the length. When I say length, well, delta x is not the length if you go like this. Okay, because if you still use b minus a over n, and this time this is your a and this is your b because it's backwards. then b minus a is going to be negative. If you do the smaller one minus the bigger one, you get a negative. So delta x won't be positive anymore. So that's the only real difference that happens if you do the integral the other way around. You're supposed to be multiplying by the length, but that's not what you're going to be doing. So in other words, when you do a definite integral, if you do the integral the other way around, it's plug in this number, multiply by delta x, but delta x will actually be negative. Then plug in this number to the function, multiply by delta x will be negative. Plug in this number to the function, multiply by delta x will be negative. Other than the negative sign, it's the length of the interval. And so that's why you get the negative of the answer if you had the numbers from 3 to 7 instead of 7 to 3. Okay, so your answer will be off by a negative sign. I want you to know that. Okay, so basically it changes the sign of the answer if you have the numbers going the other way. Delta x is the thing that changes. I want to mention it because I don't want you to think I'm lying when I say you multiply by the width of the interval. If the bottom number is bigger than the top one, you're almost multiplying by the width, but you're not. You're multiplying by the negative of the width. Okay, so that's really all I really want to say, is that I don't want to lie when I say multiply by the width. If the bottom number is smaller than the top, we're multiplying by the width. If the bottom number is bigger than the top, then we're actually multiplying by delta x, which is the negative of the width, because this is the formula that survives. Okay, b minus a over n. And of course, if the top and bottom numbers are the same, like 5 and 5, you can see right away b minus a over n would be 0. So delta x would be 0. So each term multiplied by delta x would be 0. And that's why you've learned that when you do an integral from a number to itself, you get 0 for the answer. Okay, so there's that comment. And then just lastly on this whole process, so I just want to mention it one more time, is that, what do you do? Definite integral process. First thing you have to understand is what a Riemann sum is. What does it mean? It means you cut the interval. So you're given a function and an interval. You cut the interval they give you into subintervals. Pick a number in each subinterval, plug it into the function, multiply by the width of each interval, and add that up. That's a Riemann sum. But then this limit of a sequence of Riemann sums, the idea is use one subinterval, calculate a Riemann sum, 2 subintervals, calculate a Riemann sum, 3 subintervals, calculate a Riemann sum, and on forever. Gives you a sequence of Riemann sums. The limit of that sequence, where those numbers are headed, where the Riemann sum numbers look like they're headed, is what the definite integral is. And the point that's real important, why we care, is that each Riemann sum is an approximation to something we want to calculate. Like, for example, we want to calculate a surface area. So then when you use one interval, you're making an approximation to the surface area, but it's a bad approximation. Then you use 2 subintervals, it's a better approximation. The 3 subintervals better. And the more subintervals you use, the better approximation you get to what we're trying to calculate. And so to get the exact answer, you want to take the limit as n goes to infinity of the sequence of Riemann sums. And so that's what the definite integral gives you. Okay, guys, that's the end of this video. Hopefully it made some sense. Please make sure you understand the process completely, because we're going to be applying it in a lot of different situations. And study hard.